Assalamu alaikum wa rahmatullahi wa barakatuh. This is the third video of Mechanical Oscillation Part 2. At the end of this video, you're going to be able to explain the free undamped oscillations of a compound pendulum. First, let's remember the moment of a force with respect to a fixed axis. It is given by plus minus Fd. The moment of a force is zero if the force is parallel to the axis of rotation or it intersects it. The differential equation of a simple harmonic motion is given by theta double prime plus omega 0 squared theta equals to 0. The time equation is a sinusoidal function, theta equals theta maximum sine omega 0 t plus phi. For torsion pendulum, the proper pulsation is omega 0 equals to the radical c over I. Proper period is T0 equals 2 pi radical I over C. Let's take some prerequisites first. We have studied before that the linear momentum of the system of particles is equal to the linear momentum of the center of mass of the system. And we said that the gravitational potential energy of the system of particles is equal to the gravitational potential energy of the center of mass of the system. Knowing that the center of mass of this system can be found by m1 r1 plus m2 r2 plus etc. over the total mass of this system, where r1 and r2 are the center of mass of each particle of this system. Now the question is, does the moment of inertia of the system of particles equal to that of the center of mass of the system? I will give you this example. Consider a hoop that rotates around its axis, which is passing through its center. The moment of inertia of this hoop around this axis equals to the mass times r squared. Since it is homogeneous, its center of mass is at its center, so the moment of inertia of its center of mass is 0. Why? Since r equals to 0. So we find that I of the center of mass is not equal to the I of the system of particles. Moreover, the kinetic energy is given by half I theta prime squared in rotation. We noticed that it depends on I. Then the kinetic energy of the system is not equal to the kinetic energy of the center of mass, which is 0. In addition to the sum of moment of forces acting on the system, which is I theta double prime, is not equal to that of the center of mass, which is then 0 in our case. As a conclusion, in rotation, we cannot consider the system as a particle confounded to its center of mass in studying the kinetic energy and using Newton's second law in rotation. Now, what is a compound pendulum? A compound pendulum is a rigid body which oscillates under the action of its weight around a horizontal axis of rotation which doesn't pass through its center of mass. The pendulum rotates in the vertical plane around a horizontal axis of rotation that doesn't pass through its center of mass. So it oscillates between two extreme positions, theta maximum and minus theta maximum, and around its equilibrium position. This pendulum is in equilibrium when the axis of rotation and the center of mass are on the same vertical. To study the motion of this compound pendulum, we consider a pendulum formed of a rod of mass m and a particle of mass m prime. This pendulum has a center of gravity g, which is at a distance a from the fixed axis of rotation, passing through O. In the vertical plane, the pendulum is shifted by a small angle and then released without initial speed. It oscillates then around its equilibrium position. At time t, the angular abscissa of the pendulum is theta, and its angular velocity is theta prime, which is d theta by dt. We neglect friction, so let's start with the kinetic energy. The kinetic energy at an instant t is given as half I theta prime squared, where I is the moment of inertia of the pendulum, and since it is for a system, then it is the sum of I of the wire and I of the particle. Theta prime is the angular velocity. Now switching to the gravitational potential energy. Take as the reference level of the gravitational potential energy the horizontal plane passing through G0, the equilibrium position of G. We can represent the compound pendulum by its center of gravity G, and we study the motion of a G around the axis of rotation, delta, which is passing through O. Starting with the expression, we can say that at an instant t, the center of mass is at a given position G. This gravitational potential energy is given as mgHg, such that m is the total mass of the pendulum, g is the gravitational acceleration, and hg is the height of the center of mass in meters. But how can we find this height? According to the figure, hg equals to OG0 minus OH. In the triangle OHG, we can find OH as A cosine theta, and that's because OH over OG is cosine theta, and OG is A, so A times cosine theta is just OH. Then HG equals to A minus A cosine theta, thus A into 1 minus cosine theta. So the expression of the gravitational potential energy is mg A into 1 minus cosine theta. Now the expression of the mechanical energy. The system here is the compound pendulum Earth. At any time t, the mechanical energy is the kinetic energy, which is half I theta prime squared, plus the gravitational potential energy, which is mga into 1 minus cosine theta. Finally, it is written as half I theta prime squared plus mga into 1 minus cosine theta. But you should know that for maximum theta less than 10 degrees, cosine theta can be written as 1 minus theta squared over 2. This means that 1 minus cosine theta equals to 1 minus theta squared over 2. This gives us theta squared over 2. The expression of the mechanical energy then is written as half I theta prime squared plus half mga theta squared. In order to find the differential equation of motion, we're going to start with the first method, mechanical energy. At a given instant t, the mechanical energy is constant since there is no non-conservative forces. This means that its derivative is 0. So what is the derivative of the mechanical energy? Remembering that theta prime is d theta by dt, and the derivative of theta squared is 2 theta theta prime, while theta double prime is d theta prime by dt, and the derivative of the square of theta prime is 2 theta prime theta double prime. Let's try to find the derivative of the mechanical energy then. So we can write it as half I 2 theta prime theta double prime plus half mga 2 theta theta prime, then divide by half and take theta prime common. You will find that theta prime into I theta double prime plus mga theta equals to 0, where theta prime is not 0. We can say that theta double prime plus mga over I theta is 0, and this is the second order differential equation. Now remind me with the second method. Yes, it is the Newton's second law. Choose the system. It is the pendulum. What are the forces acting on this system? The weight mg, which is vertically downward and starting from the center of mass, r vector, and it is the reaction of support. According to Newton's second law for rotation, we have sum of moments equals to I theta double prime. Then let's write the moment of each force. The moment of mg vector plus the moment of r vector equals to I theta double prime, but the moment of r is 0 since it crosses the axis of rotation. Then we have only the moment of mg, and it is minus mg a sine theta. The minus sign is just because the weight tends to turn the pendulum opposite to the positive chosen direction, and d is the distance between the axis of rotation and the line of action of the force of weight, which is equal then to sine theta times A. But for theta less than 10 degrees, sine theta is approximately equal to theta in radians. So minus mg A theta equals to I theta double prime. By arranging it, we can find finally the differential equation, which is theta double prime plus mga over I theta equals to 0. What is the general solution of this differential equation? It is of the form theta double prime plus omega 0 squared theta equals to 0. It means that the motion is simple harmonic. Then the solution is theta equals to A sine omega 0 t plus phi, or A cosine omega 0 t plus phi, where A, omega 0, phi are constants and theta maximum is always positive. Let's name the characteristics then. The proper pulsation is omega 0, which is radical mga over I. Good. What is the proper period? Good. It is t0 equals to 2 pi radical I over mga. And finally, the proper frequency is given as 1 over 2 pi radical mga over I. Let's solve this application. Given a homogeneous rod AB of length L equals to 50 centimeters and mass m, it can rotate in a vertical plane around an axis of rotation delta, which is horizontal, passing through its end A. AB is shifted by an angle theta, which is 0.15 radians from its equilibrium position, and then it is released at t equals to 0 without initial velocity. The angular abscissa of the rod is theta at a given instant t, and theta prime is the angular velocity. Take the horizontal plane containing the axis as gravitational potential energy reference level and neglect friction, given the moment of inertia of the rod as 1 over 3 ml squared. The first question is, write at a time t the expression of the gravitational potential energy of the system as a function of theta, m, a, and g. And as usual, please pause the video and think of the question. Try to solve it alone before checking the answers. For theta less than 10 degrees, we said that cosine theta is 1 minus theta squared over 2. Then the gravitational potential energy can be written as minus mg into A into 1 minus theta squared over 2. And then the gravitational potential energy is minus mga plus half mga theta squared. The second part, deduce at a time t the expression of the mechanical energy of the system as a function of theta, theta prime, I, m, a, and g. We start with mechanical energy equals to kinetic plus gravitational potential energy. Then, just write each one by its expression. Show that the differential equation that governs the motion of the rod in theta is expressed as theta double prime plus 3g over 2l theta equals to 0. There is no non-conservative forces, so the mechanical energy is constant. Now follow the steps. Now the derivative of the constant minus mga is 0. It is theta double prime plus mga over I theta equals to 0. With A given equals to L over 2 because this rod is homogeneous, and I equals to 1 over 3 ml squared, replace them with the above expression. So what do we have? Good. So it is shown. This is the end of this lesson. Try to remember these ideas and please study them well and don't hesitate to ask your teacher. This is the end of the third part. Thank you for watching.